Greetings and welcome to yet another installment of Quant Slob. This is fourth in our basic application series, this time around part 3 in our mini-series on probability sampling distributions. You recall the gym game or workout program from our installment on population parameters titled Population Proportions and Averages. This was the 13th edition in our foundational series, Lucky 13. Quick recap. This workout program involves a deck of cards. The idea is for some exercise. Say you're doing push-ups, you and your workout partner would each take turns doing sets. You would flip a card, and if the card were a queen, say, that meant you had to do 12 reps. Then your partner would flip the next card, and if he or she got, say, an ace, and they would do 14 reps, and you would each take turns until you had flipped all the cards. So that would be 26 sets each. Here is the sampling distribution of the average of the card integer ranks we just created for a sample size of 1, theoretical sample size of 1. This graph is a histogram. Histograms are used to show the distributions of quantities. They're especially useful when the domain of quantities is large. That is, the number of possible values the quantity may take is large. In this case, of course, with the sample size of 1, the domain is simply the integers 2 through 14. But as the sample size increases, the domain of possible averages is going to increase dramatically. Notice in the graph here we have a thin vertical line that marks the population average of the attribute 8. Here is the sampling distribution of the average of the card integer ranks for a theoretical sample of size 2. And what we're going to do, as we have in the past, is animate this graph to show the sampling distribution for sample sizes, in this case up to 26. And our goal is to look for a pattern as the sample size grows, particularly the width and shape of the distribution. And we see that it's centered at 8, has sort of a bell shape, and the distribution is getting narrower and narrower as the sample increases. This is jumping way ahead here, but I want to spend a moment on this. If you were playing this gym game, just hypothetically, and you started with a well-shuffled deck of standard playing cards, would you be surprised when you were done if the average number of reps that you did per set, or should have done based on the card's integer rank value, was, say, 6 or less? And by the way, just in passing, if you're interested in learning about histograms, because there's a lot to them, the Wikipedia page and also mathisfun.com topic are both very good, I think. For another example, let's consider the infinite imaginary population of every possible toss of a coin. We're going to assert that the population parameter proportion of heads is precisely 1/2. We're defining it that way. So let's take a look at the sampling distribution of the proportion of heads in a theoretical sample of size 1. Note we're back to using our line plot or line height plot to graphically show the distribution of these quantities here. Here's the sampling distribution of the proportion of heads in a theoretical sample of size 2. And as we have in the past, we're going to take a look at the probability sampling distribution animated for increasing sample sizes. This is going to be playing faster than in the past because we're going to count all the way up to a sample size of 500. What's the pattern? Well, like in previous examples, it's centered, or appears to be centered at the population parameter 1/2. It's bell-shaped. It gets narrower as the sample size increases. If you have a very fine eye, you'll notice that the rate at which the distribution narrows slows. You'll see here that the sample size counter, is rolling forward at a steady state, but the rate at which the distribution narrows slows, slower and slower. Till finally we get to 500. You can see, in fact, at this point, the rate at which it's narrowing is almost very hard to detect as the counter rolls up. To close out this edition, we're going to replay the previous animation, but with one difference. Here, we're dynamically changing the scale of the x-axis. Basically, and you can see this here, we're progressively zooming in on the x-axis as the sample size increases. And this zooming or rescaling of the horizontal plot region we're doing here, and you can see that down there, is being done in a very particular mathematical way. And what do we see? In the previous version, we saw the distribution get narrower as the sample size increased. But here, the general shape appears virtually unchanging. And once again, if you have a very fine eye, you'll notice that the rate at which the abscissa, or the horizontal axis, is expanding is getting slower and slower as the counter, the sample size counter in the animation increases. And that's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.